Third announcement, on the main website for the course there is a sample midterm. So if you go to the main website you'll find a sample midterm. Our midterm will be pretty much like this. I mean, I just looked at it, it contains six questions. Some of the questions have several parts. So questions are pretty simple, I would say, so basically the same format. Okay, so any questions about these changes? Yeah. Next quiz, yes, next quiz is on Thursday, once again, last 10 minutes of the lecture.
So does it cover the material that was already covered, right?
No, only the new material. Other questions? Okay, so today I want to talk a little bit more about derivatives. I'll start with reminding you how to sketch a graph of derivative given a graph function. And last time we've seen some of the features, so I'll summarize what we've seen already. You know that if a function is, so first of all, the derivative is qualitatively fixed. It is the slope of the tangent line. How steep is the tangent line? How fast is the function growing forward? So if the function has horizontal tangent and such picture, or picture like this. In all these cases, this will correspond to zero of prime, right? Horizontal tangent means slope of the tangent is zero. Well, if my function is increasing, so points in this direction, what can I say about its derivative? Positive, right? Similarly, if it is decreasing, points in this direction, well then we have the derivative as negative. And we also have seen some more features. If the function is trending upwards, like this, or like this, so trending upwards, what happens to the derivative? So the slope starts from here in this graph and eventually it increases. It starts from here and increases. So here it's increasing. And similarly, if you flip this picture, if the function is bending downwards. The derivative is decreasing. So let's have some quick examples. If my function looks like this, what can I say about its derivative? Okay, so here lots of information. Is it positive or negative? Positive, right? The function is increasing. Well, somewhere here it might be about 1, so let me put the point somewhere here. Is it increasing or decreasing as we move to the right? Decreasing, right? Here it is something, but then it becomes smaller and smaller. So it is decreasing from here. But it's always positive, so it looks somewhat like this. As you move to the left, it is, well, the derivative becomes steeper and steeper. And, well, right near this point, we see that the tangent seems to be vertical. So at nearby points, the derivative will be pretty large. So we should draw something like this. Well, and if we're interested in just qualitative data, we don't know what the function is, well, that's about how far we can get. Another example, such a function. What happens to such a function? Is the derivative positive or negative? Positive, because the function is increasing. Is it increasing or decreasing? Increasing. So we see we are in this situation. So the function's derivative is increasing, and moreover, when x is very negative, it seems that the derivative is almost 0. Not exactly maybe, but close. So it starts from being close to 0, and then eventually it increases. So some graph of this kind. Once again, you can't really be more precise than this, just given this information. Let's try such a proof. My function will look like this. What can we say here? Well, let's start from the maybe let's start with zeros of the derivative. They're pretty easy to locate usually. So my derivative will become 0 when I have a horizontal tangent. In this example, well, I see here I have a maximum, here I have a minimum. The tangents are horizontal at these 2 points. So corresponding to them will be zeros of derivative. And you see no other zeros, no other horizontal tangents. Let's see. In between these 2 zeros, is the derivative positive or negative? Negative, right. It decreases. Sorry, it is negative. So somewhere in this territory. Before this, it is positive, because from here to here, the function is increasing. So somewhere in this territory, and from here to here, it's once again increasing. So the derivative is positive. Well, for now we just know this part. It's positive, negative, positive. Let's be more precise. In this part, is it increasing or decreasing? Decreasing, right. We have more or less such a behavior. All the way up to here, it's bending down. It's decreasing and becomes negative here. So here it is decreasing. And we start from a value of, well, 1, 2, some reasonable values. We should start somewhere here, and make the function decrease all the way up to here. From here to here, my function will advance in the opposite direction. The derivative, the slope becomes less and less negative, and then it becomes positive. So it increases from here. So the derivative will look somewhat like this, and once again at this point it will be reasonably positive. 1, 2, not huge, not small, something like this. So that's about the graph of derivative. We can't be sure how precise it is. I mean, it might be like this, or it might decrease slightly slower, slightly faster. Well, we have some freedom here. But, well, that's qualitatively how it will look like. If we had the actual function, well, we would have better estimate what is the derivative. Okay, so questions about these examples? Yeah?
The first example, when it's like straight only onto the f, does it mean that you're basically the slope is right?
So here, the vertical line, the slope of vertical line, slope of 1 is 45 degrees with the x-axis. But slope of larger than this is like this. It approaches infinity. Yes. Other questions? Okay, so let's try a little bit trickier one. My function is of this shape. First, a line like this, then it continues to be aligned with the same slope. I hope that I can make a parallel line. And let's say here it is right here. So this is x, this is f. What can we say about the derivative? So first of all, let's forget about this point 0. There is something strange happening at 0. What is the derivative when x is say negative? Well, yes, it is some constant number. It might be 1, might be not exactly 1. I didn't tell you like what are the values, what is the scale. But, well, it is some number, it is positive, my function is increasing, and it looks constant because the tangent line at all the points is the same tangent line. It has the same slope. So I would draw something like this, a constant number. Well, I tried to make this line parallel to that one. I hope the picture does show it as parallel more or less. So when x is positive, I will still have a line with the same slope. Now it's tempting to conclude that the derivative is identical or equal to this constant. Well, we should think a little bit. Because at the point 0, what is the tangent line to this graph, to the graph of this function? Is it this line? Well, it approximates this part of the function pretty well, but it's pretty far from this part of the function. And also it's not this part, this line. I mean, it approximates the function pretty well here, but not here. Maybe it's the vertical line. Well, it's kind of hard to decide with just a picture. Let's compute it using the actual formula. Let's try to come up with an example of a function whose graph looks exactly like this, and use the very definition of the derivative. So, example function. Such graph. So can anyone give me an example of a function whose graph will look like this? X plus 1. Okay. So just x plus 1 would look like a straight line without any breaks. but I do want a break. I want this to be, so x plus 1 describes pretty well the function right here. I would want this to be only for x which is positive, in fact greater or equal than 0. I want at the point 0 to be positive. But when x is negative, I will want a different function. What function? Right, exactly. So I'll take x minus 1 because I want the same slope. So I'll take the same multiple of x, but now use different y-intercept. So x minus 1. When x is 0, I want this to be negative. Okay, pretty reasonable function. Next, well, it's obvious that f prime is 1 for every x which is not equal to 0. So f prime x is equal to 1 for x which is not equal to 0. What's interesting is what is f prime at the point 0. By definition, it is the limit as x approaches 0, f of x minus f of 0 divided by x minus 0. Well, let's see. Which definition of f I will use? I'll have to separate the two cases. One for limit from the right and one for limit from the left. So one of them, when x is bigger than 0, I'll use this formula. When x is smaller than 0, I'll use that one. So let's compute separately limit from the left and limit from the right. X minus f of 0 divided by x minus 0. What is it? It's limit as x approaches 0 from the left. F of x. So here my x is smaller than 0. I approach 0 from the left. It means I'm close to 0, but, well, still smaller than 0, still negative. So I'll use this definition, x minus 1. What is the value of my function at the point 0? Negative 1? Well, no. If you look at this function, how is it defined? It's defined to be x plus 1 when x is greater or equal than 0. So in particular, when x is equal to 0, it's defined to be 1. The very definition of this function tells you f at the point 0 is equal to 1. It doesn't matter that here I'm computing the limit of as x approaches 0 from the left and so on. That's not, I mean, it does matter for the value of f of x, but not for f of 0. 0, well, f of 0 is just the value of the function at the point 0. It's not about any limits. So the value of function at the point 0 right here is 1 divided by x. Okay, so this is x approaches 0 from the left, x minus 2 divided by x. So if I look at these numbers, what do I see? When x is small or negative, 0 minus x minus 2 is close to minus 2, and denominator is small negative number. So I'm dividing negative 2 by small negative number. It means that I get huge numbers. Because, well, if you divide minus 2 by, say, minus 0.00002, you get, well, 10 thousandths. If you divide by minus 0.0000002, you get, well, no, million, 10 millions. So this, well, for now we'll say it's not defined, but later we'll say plus infinity, or does not exist. So in either way it's correct for now. Yes?
Yeah, with that e plus 1 instead of minus 1, because you're using 0 minus, which means just that 0, right? And that's minus 1.
Okay, so once again, the value, so let me explain what happens here. The value of my function at the point 0 is not about computing any limits. My function is just a device for taking a number and outputting a different number. And the rule according to which it operates, well, if the number is greater or equal than 0, then the output is x plus 1, and so on and so on. So if my number, my input, is equal to 0, my function uses this formula. It doesn't matter in which context I use this number. I might use it in computing limit from the left. I might use it in limit from the right. But it's just the value of the function at the point 0. The place where the context does matter is here for f of x. When x is close to 0 but negative, what is f of x? Well, if x is negative, f of x is like this. Okay? So this number is 1, not minus 1. Okay, so in either way, we already see that the derivative does not exist. And we can actually see it on the graph. I mean, now that we have seen what happens with the definition of derivative, we can see it on the graph. Value of the function at the point 0 is right here. For nearby values of x, well, there's no problem with x which is sliding to the right. If you approach this from the right, the slope of the secant lines will be constant 1. Maybe if you don't really believe this, we can compute the limit from the right. F of x minus f of 0 divided by x. Well, now it will be, I will use this definition, x plus 1 minus f of 0, which is, of course, still 1, and it is 1. So there is no problem with approaching this point from the right. But if you take x which is smaller negative, somewhat like this, then f of x is right here. And then you try to approximate the tangent line by secant lines like this. This secant line, this one, and you get closer and closer. So of course the slope gets more and more steep. It gets closer and closer. Well, it becomes larger and larger. That's why I say here it's kind of plus infinity. So the secant lines here, well, they start from here and then become more and more vertical. And you see that, of course, my derivative doesn't exist at this point. So we'll have to say that f prime at the point 0 does not exist. No value for f prime at the point 0. Okay, so maybe any questions about this example? Okay, more generally. More generally, we can consider the following question. Is it necessary for a function to be continuous at a point for it to have a derivative? So here we see a function which is discontinuous, and, well, as a consequence, it seems that it doesn't have a derivative. Is it the general case? So, question. If f has derivative at x equals a, must it be continuous? So once again, here we have a function which doesn't have a derivative at some point, but it seems that it doesn't have a derivative because it's not continuous. So the question is, well, at the points where it does have derivative, must it always be continuous? Yeah.
That's not true. We only use x plus 1 when x can't equal to 0. Use that formula and that assumption.
Okay, so we say that if I change this equality and move it to here, I will get.
Just use x plus 1 and then x not equal to 0. That would be the derivative. You can have x. You can have
You say f
derivative
of x is x plus 1, then x is not 0.
Yeah.
This.
and
And
that's,
when x is 0.
yeah, so you can draw it out. It would be like a dot in the middle. So at that point there would be a derivative, but then it's not continuous.
Okay, actually not quite. So if for such a function, it looks like this, right?
Yeah.
You can't even ask the question of what is the derivative at this point, because according to our definition, it must be f of x minus f at 0 divided by x minus 0. But you see, f at 0 is just not defined. Alright, so prime at 0 still does not exist. So that would not be a complex sample. I mean, I see what you mean. Kind of, it looks like it has
Yeah.
a tangent line at this point, but so according to our definition, it doesn't. It's pretty good. Okay, so the intuitive, well, how would we argue about this? At least intuitively, we'll say it like this. If a function has a derivative, it means it has tangent line. It means that near this point it looks more or less like a straight line. Well, small deviation from a straight line, but pretty much like a straight line. Would it necessarily mean that f is continuous? Well, of course, because if you change the parameter x slightly, f of x will just change, well, in a manner like straight line changes. Very continuous, very nice. So at least intuitively we would expect actually that this is correct. And to be a little bit more precise, let's see, well, what is this according to definition? So answer yes, and the reason is if f prime a exists, what does it mean? It means that the limit of f of x minus f of a divided by x minus a as x approaches a exists. Now, how is it possible? How would it be possible for such a limit to exist? Well, you see, you divide some numerator by some denominator which approaches 0. But still, such a quotient does exist. What does it say about the numerator? So once again, you have a limit where the numerator, well, we just don't know what it is for now, but the denominator tends to 0, becomes smaller and smaller. You divide some number by a very small number, and somehow in the limit you do get some particular number. Well, the limit does exist. What does it say about the numerator? Can it be close to, say, 5? Well, of course not. If you divide 5 by a small number, you get huge numbers. Same about minus 5. If you take minus 5 divided by a small number, you get, well, negative huge numbers. The only way for this limit to exist is for the numerator also to be small. And then, well, not always, but at least it's possible for a quotient of small number by another small number to be close to some particular value. So, if such a limit exists, in particular, the numerator f of x minus f of a must approach 0. Just no other way. But that means exactly that the limit as x approaches a of f of x is f of a. if the difference is close to 0, this must be close to this, which means i.e. f is continuous. So you see, this intuition actually does translate to actual, well, argument that shows that yes, it must be continuous. So now maybe the more interesting question is it possible for a function to be continuous but not to have a derivative? So can if f, so now the question, if f is continuous, at some point x is a must have a derivative. X equals a. So let's ask the opposite question. Suppose that I know my function is continuous. Suppose I can draw its graph without lifting my pen off the paper. Must it be true that it has a derivative? Must the graph have a tangent line at any point? No. Why not? Yeah?
Absolute value of x comes to a single point, but it doesn't have two different slopes.
Exactly. Yes. So the answer is no. It must not be differentiable. An example. Let's take f of x, which is absolute value of x. What happens with this function? It looks like this. It is a straight line up to 0 and a different straight line after 0. So it is continuous. I can draw it without lifting my chalk off the board. No problem with it. What about its derivative? Well, here it is -1, the next is negative. The next is positive, it is +1. But exactly at the point 0, it seems that we are not sure. Is it -1? Is it +1? Is it something in between? So let's actually check with the definition what is the derivative at 0. So let me write f prime of x is -1 for x negative. F prime of x is +1 for x positive. And let's argue. Let's find out what is the derivative at the point 0. Well, by definition, once again, its limit as x approaches 0, absolute value of x minus the value of the function at 0, which is absolute value 0, divided by x minus 0. So it's the limit as x approaches 0, absolute value of x divided by x. And that's exactly our favorite example of a limit which does not exist. From one side it's +1, from the other side it's -1, so this thing does not exist. So f prime at the point 0, well, it's not +1, it's not -1, it just does not exist. So to summarize, well, if a function has derivative, then it must be continuous. But in the opposite way, if it is continuous, it still might not have a derivative. So let me write it like this. Differentiable implies continuous. differentiable is just a word for has a derivative. But not the other way around. The function might be continuous, but have corners. So exactly like this. So such a function would not have a derivative at the point. You might imagine some other corners. More smooth corners, but still corners. So such examples are bad for the derivative. So maybe questions about this relation of differentiability and continuity. Okay, so So next part of the lecture is about just computing some derivatives, and well, I mentioned that for kind of the vast majority of you it will be a review of high school material, not just nothing new, but still we will discuss it. So computation of derivatives. Let's start with examples. F of x is constant 5. For every value of x, then f of x is 5. What is the derivative? Right, it is 0. You can either imagine a horizontal line at height 5, so its slope is 0, or you can compute it by definition. F prime of x is limit f of x plus h minus f of x divided by h, so h equals to 0. But what is it? It's 5 minus 5 divided by h. So it is 0. Either way, well, obviously this derivative is 0. More generally, if f of x is some constant, well, 17, pi, whatever constant, its derivative is 0. Same reason. So c is a constant number. Let's try something more tricky. F of x is x cubed. So before I continue, how many of you do not know what is the derivative of this function? Okay, good. So the derivative is, as you all know, 3x squared. My point here is, well, yes, in the end we'll just use this formula, but for now let's see whether it follows from the very definition. So f prime of x is, by definition, limit as h goes to 0, my function evaluated at x plus h, so x plus h cubed, minus my function evaluated at x, divided by h. So how do we evaluate such limits? Well, when h is small, the numerator approaches 0, denominator approaches 0, so we should do something. What can we do? Sorry? Expand, right. So let's do some algebra. Let's just open the brackets. So it's limit as h approaches 0. X plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed from here divided by h. So what I did, I just used the formula for what is a plus b cubed. A plus b cubed is a cubed plus 3a squared b plus 3a squared plus b cubed. If you happen not to remember such a formula, well, you can just take 3 brackets, a plus b times a plus b times a plus b. And slowly, carefully, just open 2 of them, then open the third one. So either way you'll find this answer. Okay, so now let me continue. That is just a remark. From here, I get that this is limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed divided by h. Now I can cancel out the h. Limit as h equals to 0 of 3x squared plus 3x h plus h squared. And well, as we expected, when h is close to 0, this whole thing is close to 3x squared. So no surprises in the answer, but I did want to show such a computation. Because on the next step, I'll try. So maybe any questions about this computation? Yeah.
Just a quick question. Say on the picture you give us a question that you can how
Yes. So you definitely can use all the correct formulas like this from algebra. Yes.
yeah, but we don't have to compute at the moment, right?
No, no. Other questions? Okay, so the next question is can we start with the definition of derivative to find out what is the derivative of x to the power n, but where n is any integer. So next question, f of x is x to the power n. And n is positive integer. Well, once again, we can apply the definition and say that derivative is the limit as h approaches 0 by function of x plus h, so x plus h to the power n minus x to the power n divided by h. Next step would be, well, as before, open the brackets. In this example, it's a little bit more complicated expression. It's x plus h to some power which we still don't know. It's n. It's not 3, it's not 5. We can't choose just this method. But well, fortunately, we also don't have to actually expand all the brackets. Because look at the previous example. What happened in the previous example? After we expanded, the first term without the h, well, it got cancelled out. That's what we expect here. We'll have x to the power n, will get cancelled out as x to the power n. Next term was kind of important. It survived to the very end, and here it appears. But all the terms afterwards, they contain h to the power of 2 and bigger. So this was h squared, h cubed, and so on. Well, even if you divide it by h, we still get in the quotient something times h, something times h squared. But then we take h goes to 0. Then we take h which is very, very small. So all these terms we don't really measure. So what we should understand about this thing is just this part. What is x plus h to the power n? We want to understand that it's x to the power n plus, well, some number is x to the power n minus 1h, and plus some other terms which we don't, well, they're not important. So this will be not important. Because it has h to some power which is at least 2. And even if you divide by h, after you take h goes to 0, they will just disappear. So luckily for us, we don't need all the expansion. We just need basically one term, this one. And it's not that hard to figure out what is this term. If you take x plus h, you multiply it by itself n times. Well, what is it? Suppose you can take x from each of the brackets and get x to the power n. Well, alternatively, you can, well, how can you get just one h and all the rest x? Well, you can choose the h from any one of the brackets. From the first one, h times x, 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 or you can choose x, h, x, 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 or, well, and so on and so on. So basically, you just choose one of the brackets with h, and in the rest you take x. So you have n choices. And once again, I don't care about all other terms. They have h to even larger power. So let me continue with this thing. So limit as h goes to 0, x plus h to the power n minus x to the power n divided by h. Limit h equal to 0 of, well, n x to the power n minus 1 h plus other stuff divided by h. And this other stuff contains large powers of h. So it's the same as limit as h goes to 0 n x to the power n minus 1 plus things which contain h. So all these things contain h. So as we take h smaller and smaller, they will just disappear. And the answer is n of x to n minus 1. Well, so in a way, my point here is not really about the answer. I hope that you actually do know what the answer is. If f of x is x to the power n, the derivative is n x to the power n minus 1. So, first of all, you should definitely know this point. But my point is like this. It's not that this formula is something kind of additional information that we didn't know before. In a way, we did know it. We knew the definition, we knew how to open the brackets, so in a way, we didn't know this result. Well, of course, it wasn't immediate to get this result. So, well, we worked a little bit, and we actually got this result. From now on, we'll never rederive it. We'll just use the answer. But the point is that it is possible to derive. It's not something like it does. I mean, this answer doesn't come from your teacher, your book. Well, it just. I mean, it must be the answer. Here's its derivation. And well, so basically, we'll derive several results and forget about the derivations completely. what we expect from you kind of on homeworks, midterms, exams, is just to be able to use the definition in these simple cases. To find derivative of x cubed, maybe x to the fourth. So open 3 brackets, maybe 4 brackets. Not more than this. Such computation is, well, a little bit beyond what we expect from you. So you're not expected to be able to really apply binomial formula or open n brackets where n is unknown. So this is just a little bit beyond what we expect from you on midterm or exam. But you should be aware that it is possible. Okay, so any questions about this derivation or in general what's expected of you or any questions? Okay, so we got this formula. We even derived it for n which is integer, but actually this formula works more generally. So this formula works for n at any value, not necessarily integer. Let's see how it works. Well, of course, in simplest cases, you'll see such expressions. X to the power 100 is derivative. Well, just plug in inside the formula. So no problems. But it is more general than this. You can compute what is the derivative of square root of x. So let me write this as x to some power. What power? 1/2, right. And now I can use this formula. It's 1/2 x to the power 1/2 minus 1. So it is 1/2 x to the power minus 1/2. So it is 1 divided by 2 square root of x. Okay, another example. Derivative of 1 over x. Same trick. I will write 1 over x as x to some power. What power? -1. Right. X to the power -1, its derivative is -1 times x to the power -2, which is -1 minus another 1. So it is -1 divided by x squared. Maybe one more example, and then we'll talk about other stuff. So we'll say cubic root of x squared. Derivative of this function. Still same trick.
Yeah.
I can write this as x to some power. What power? Yes, so maybe let me do it slowly. It's x squared to the power 1/3. So it is x to the power 2/3. So you see, I'm using my rules for taking powers. So it is 2/3 x to the power -1/3. So it is 2 divided by 3 with the roots of x. Okay, very good. So we should definitely be familiar with this formula when n is integer, when n is not integer, how to apply it in any case. Let's see some other formulas. So next thing is about f of x, which is e to the power x. I'll take exponential function. So the derivative f prime at the point x, once again, for the very first time we will see derivation. At least we'll see that derivation is possible. So this is by definition the limit as h goes to 0 of my function raised at the point x plus h, so e to the power of x plus h, minus e to the power of x divided by h. If you look at this limit, we see that when h is small, numerator is small, denominator is small, we'll have to do something. Well, we'll do some algebra. We'll rewrite this e to the power x plus h as e to the power x times e to the power h. So we continue here. So this thing, e to the power x plus h minus e to the power x minus h, and rewrite limit as h goes to 0, e to the power x times e to the power h minus e to the power x divided by h. Well, I can factor out this e to the power x. Its limit as h goes to 0, e to the power x, e to the power h minus 1 divided by h. So here, this part of expression doesn't have inside of it h. It's not changing as h changes. It's just some number for us. I mean, 5, 17. It does not depend on h. So basically I can take it out of the limit. It has nothing to do with the limit itself. So it's e to the x, and what's left is the actual limit as h goes to 0 of e to the h minus 1 divided by h. Okay, that's very good, but the problem is we still don't know what this limit is. What is it? When h is small, numerator is small, denominator is small. How to go about it? Well, turns out it's a pretty hard limit. But what is its meaning? Its meaning is, well, if you look at the function e to the power x, it looks like this. What is its limit? Well, when h is small, we take a point h, here is e to the power h, and here is 1. So the difference e to the power h minus 1 is right here. So this is e to h minus 1, and this is precisely h. So it is the slope of such a line. And when h becomes smaller and smaller, it becomes the tangent line. So this thing is slope of tangent to y is e to the power x at x equal to 0. But now we do know what it is. Recall that maybe in the second lecture, third lecture, we defined the number e to be such a number so that such a base so that the tangent line at the point 0 to its graph is equal to 1. If you recall, we made a computation with slope of tangent of 2 to the power x, and we said it was a little smaller than 1. For 3 to the power x, it was a little bigger than 1. And we said, well, for some number in between 2 and 3, it must be equal to 1. And we denoted this number to be e. So this thing is 1, basically by our definition of the number e. By our definition. I realized that it might be a little bit confusing because, I'm referring to a lecture kind of 2 weeks ago. So you might have already forgotten how they actually define the number if. But anyway, if you go back and check, that's exactly how we defined it. We chose it so that the tangent to this graph will be equal to 1. And now we have a very nice kind of corollary from this. We say that the derivative of e to the power x is e to the power x times 1, so it's e to the power x. So with this particular base, this exponential function has very nice behavior with respect to derivative. Its derivative is the same function, doesn't change. It will not work for any other base, only for the base e. If you take 2 to the power x and take its derivative, well, it will still be 2 to the power x, but times, some more complicated number. The slope of the tangent line to 2 to the power x, which is more complicated. So once again.
That's not the end.
Sorry?
No.
So once again, you are expected definitely to remember this formula. Derivative of e to x is e to x. You are, sort of expected to understand what happens here. At the very least, you should be able to go from the beginning to this line. On a midterm, for exam, they'll probably not ask you to derive such a thing. So probably it's a little bit beyond what can be asked on an exam. They can ask you something like derive the equations for derivative of square root of x or x cubed. That is, this part is kind of okay. So for simple functions, yes. For more complicated, probably no. Okay, so maybe any questions about derivatives that we know so far? Okay, now we can basically derive x to the power n, e to the power x. Next part is, let's combine several of them together using the favorite operations. Plus, minus, product, quotient. Okay, so we'll introduce several rules for derivatives. If f and g are differentiable, then derivative of their sum is the sum of derivatives. Derivative of their difference is the difference of their derivatives. And if you take any constant number and multiply the function by a constant number, well, you take the constant out. C is a constant number. So let's start with these simple rules. So they say, basically, with respect to very simple arithmetic operations, plus, minus, and multiplication by constant, the derivative behaves very, very well. Basically, we can do it in any order. take the sum, then take derivatives, or take derivatives, then the sum, it doesn't matter. So, for instance, examples, if you take x to 100 plus 5 over x plus e to x, and you compute the derivative, holding minus e to x. So if you start with this expression and you take the derivative, well, first and second rule tells you you can instead take derivatives and then make the operations. So the derivative of x to 100 plus derivative of 5 over x minus derivative of e to the power x. Next part, well, here we already know what is the answer. It's 100 x to the power 99. For this one, well, let's take the 5 out because we are in this situation. It's a constant times a function which we know how to derive. So it's 5 times derivative of x to negative 1. And finally, derivative of e to x is e to x. Okay, and finally, last step, we compute the derivative of x to negative 1, which you already remember is minus 1 over x squared. So it is minus 5 over x squared minus e to x. So basically, very simple rules, very simple, very easy to apply them. If you see a familiar function times a constant, well, take the constant out. If you see sum of two familiar functions, well, take derivatives of both functions and then take their sum. Say again? Yeah, so you would have left the answer this way. I mean, you would write it like this. Plus 5 times negative 1 times x to negative 2 minus e to x. That's also correct, but it doesn't look kind of finished. I mean, it asks you to simplify this expression. So I would say such a form is more familiar. So, I mean, if you have time, try to simplify these derivatives. If they look really terrible and you have no idea how to simplify them, well, just leave them and make sure they're at least correct. Okay. So questions about these two rules? 3 rules. So these ones are the simple ones. More complicated ones are about the product and the quotient. So let's introduce what happens with products and quotients. By the way, once again, these rules, they don't fall out of the sky. They can be derived from very definition. It's just we don't have much time to do this. But it's not complicated to actually show that these rules must hold. Same about these rules. So, additional rules. If you take derivative of product, turns out the answer is like this. It's derivative of f times g plus f times derivative of g. And if you take derivative of quotient, it is f prime of x g of x minus f of x g prime of x and divided by g squared. So it turns out derivative doesn't behave in a very simple way with respect to products and quotients. That's the way it behaves. If you take derivative of product, the answer is like this. If you take derivative of quotient, answer is like this. So kind of the way people usually remember it is fg prime is f prime g plus fg prime, and f over g prime is f prime g minus fg prime divided by g squared. So that's more or less the way I remember. Once again, it's not that, I mean, somebody sat down and decided let's have such and such rules. No, it also can be verified from the very definitions of derivative, but well, once again, we don't have time for this. So we have just some examples. Let's compute the derivative of x times e to the power x. Well, we see that it's not one of the familiar functions, but it is a product of two very familiar functions. So we'll use this product. So the answer is first function derivative times the second one plus first function times e to x derivative. Well, what is the derivative of x? Let me maybe write it like this so that you won't confuse it with x to the power 1. It's x derivative. So yes, derivative of x is 1. You can, well, either imagine a line at slope 1 and say that its slope is 1, or you can say that it's x to the power 1, and hence the derivative is 1 times x to the power 0, which is 1. Either way, it's 1 times e to the power x plus x times derivative of e to x, well, it's just e to x. So it is 1 plus x times e to the power x. Let's try another one. Let's try square root of x. Let's try e to the power x divided by square root of x. So once again, well, one way to solve this is to recognize that it's a quotient of two familiar functions. So we'll apply quotient. By the quotient rule, it's derivative of numerator times denominator minus numerator times derivative of denominator divided by denominator squared. Well, we still have derivatives, so we still didn't get the answer, but we can get to it very fast. Derivative of e to x is e to x. Derivative of square root of x is 1 over 2 square roots of x. And square root of x there is x. So if you just want to compute the derivative, this might be enough. If you want to compute the derivative and also work with it later, then you might want to simplify. So it depends on the actual question. So you might do it like this, or you might well continue and write that it's e to the power of x times square root of x minus 1 square root of x over x. And you might even want to simplify it a little bit more. It depends on what you actually want. I mean, this is already an answer. It doesn't involve any new derivatives, so it is an answer. And well, just a comment, we do expect it to be able to derive many functions, which means find their derivatives fast. Because we see our, for example, even our midterm is, well, it's just 50 minutes and 6 questions. So you should realize that we ask you to solve, not just to solve questions, but solve them fast. So you should train yourself to actually compute derivatives fast. Guys, we didn't finish yet. So it wasn't a call for a discussion about, well, how long is a meter. It was just a comment. Okay, and of course we might get even more complicated expressions. For example, something like 1 divided by 1 plus x squared e to x. It doesn't have to be a quotient of just two familiar functions. It might be a quotient of products, of sums, of quotients, and so on. It might be a composition of all the separations in, well, any number of them. So for example here. But still we take kind of the last operation that we did a quotient, and we apply the quotient. So it will be derivative of 1 times 1 plus x squared into x minus 1 times 1 plus x into x derivative divided by denominator square. X squared. Well, that's not yet the answer because we see there are two derivatives in the answer. But we can, well, get closer. We can compute the derivatives. What is derivative of 1? 0. Exactly. It's a constant. Its derivative is 0. So all this thing is just 0. Well, this is 1. And then we have to find derivative of this thing. Well, we have some expressions, so it is minus derivative 1 plus derivative of x squared into x. Divided by 1 plus squared x squared into x. Okay, still not the answer, but very close. Now we have just very simple derivatives. 1 prime and x squared into x prime. So let me continue maybe here. Derivative of 1, we already know it is 0. So first thing is minus, well, let me write it 0 plus x squared e to x. Well, I'll use the product rule. It's a product of two simple functions. So it's x squared prime e to x plus x squared e to x prime. 1 plus x squared e to x squared. And only now we can find the actual answer. So it's minus 2x e to x minus x squared e to x divided by 1 plus x squared e to x squared. So you see that such a computation is a little bit longer. I mean, we might have made it a little bit shorter by doing parts of it kind of in our head, but still, this kind of many steps. But every step is very simple. Just application of one of the rules. Product rule, quotient rule, sum rule, x to the power n rule, or e to the power x. So each step is very, very simple. It's just about combining enough of them and not making a mistake. So it's okay, see you next time.